Welcome to Unit 3 of our lectures in synchronization. This one is about locks. The learning objective for this lecture is first, to learn how to apply locks to eliminate race conditions in a multi-threaded application, and second, to understand some of the difficulties in implementing locks. We'll talk more about these during the lecture itself. So first of all, let's learn what a lock is. A lock is an operating system structure that has two states. It can be held. This represents the case when a thread is in a critical section and no one else should enter, or not held, which means the critical section is not currently in use and a thread can enter the critical section. To represent these two states, there are two operations to move the lock between the states. The first is the acquire operation. When a thread calls acquire, it marks the lock as held if no one is currently holding it and allows the thread to proceed by returning immediately. If a thread has already called acquire, then the acquire operation does not return, but instead waits until that first thread that called acquire subsequently called release. Release therefore marks the lock as not held and lets one other thread that is currently calling acquire proceed. This means that if many threads call acquire, at the same time only one thread can get through and hold the lock. All the other threads will keep waiting until the first thread calls release. At that point, one of the waiting threads will return from acquire and keep going. When that thread, the second thread, calls release, it will allow a third thread to make progress and so forth until all of the threads have returned from acquire and can enter the critical section code. So how do we use locks? Well, first of all, locks are usually declared like a variable. Most programming languages or operating systems have a lock data type that you can use to declare lock variables, as in the example here, lock L. Furthermore, a program can have multiple locks, so you might have two locks named L and M, and a program can then, when it acquires a lock, will explicitly say which lock it wants, lock acquire L or acquire M. To use a lock within a critical section is simple. Put a call to acquire a lock at the start of the critical section. This makes sure that only one thread can enter the critical section at a time. Put a call to release at the end of a critical section. This allows other threads to enter the critical section because this first thread is done. This achieves our requirements of mutual exclusion and progress for implementing critical sections as we described in the previous lecture. One thing to note that's important though is that acquiring a lock only blocks other threads trying to acquire the same lock. So if one thread acquires lock L, it doesn't stop another thread from acquiring lock M and vice versa. It will stop threads that want to acquire lock L though. This means that we can have different threads in different critical sections at the same time. The question then comes up is, well, is it safe to have different locks protecting different critical sections? What if we need to stop all threads? Well, the thing to remember about using locks is that you have to use the same lock for two critical sections that access the same data. This means you might have different functions that access the same data, such as a withdraw function and a deposit function for a bank account that use the same lock. This is important because we want to make sure that while we're doing a withdraw, nobody does a deposit and modifies the bank balance. So this means that we need to use the same lock within the withdraw and the deposit function. However, if you have a withdraw and a deposit function and then another function to print the hours the bank is open, we don't need to use the same lock we use for withdraw and deposit on the function that prints the bank hours because that's accessing different data. It's not accessing the bank account balance. So let's see how we'd use this in a code. Recall our example from before of the bank transaction and the code to do the withdraw. We said there was a critical section where we read the old account balance, modified it, and wrote back a new account balance. To protect this critical section with a lock, we'd put a call to acquire lock before entering this critical section and a call to release a lock when we're done in the critical section. We don't need to hold the lock once we're done modifying the data because after that we're just accessing a local variable, in this case the balance variable. So let's look at how this works. Suppose we start with an account balance of $100, and again we'll have the pink and green threads. The pink thread enters, calls acquire on the lock, and begins updating the balance. When a green thread enters and then tries to call acquire, it will be stalled. It'll be stuck here inside the acquire function until the pink thread calls release. The pink thread can then start executing again, update the balance, and call release, leaving the balance at $90. At this point, and only at this point, is the green thread allowed to run again. When it runs, it sees that the balance is $90 as it should be. It updates the balance to $70 and then releases the lock and returns. At the end, the bank account balance is $70 as it should be. Now let's look at what happens if the green thread runs first. In this case, it will call acquire on the lock. It'll update the balance to be $80. When the pink thread starts running and calls acquire, it will again be blocked and won't be allowed to run until the green thread calls release. Only after the green thread calls release and updates the balance to be $80 can the pink thread start running. It will see the balance is $80, subtract $10, update it to $70, release the lock and return. In this way, no matter which thread runs first, we have the same balance, which is $70. This means that we don't have a race condition anymore because we don't have code that depends on which thread runs first. Without the locks, we had a race condition where we could get different values depending on when the threads ran. So how do you implement locks? Well, a simple way to do it would be to have a lock be just a Boolean variable. When we're trying to acquire a lock, we can just sit in a while loop reading the lock variable and waiting until it's set to false. So lock arrow held is not true and the while loop drops out. We could then send lock held to be true. This would very simply just sit there in the while loop while anybody is in the critical section, and after another thread calls release and sets the held to false, this while loop will drop out and we can update the lock. So this seems like a very reasonable way to implement locks. However, it doesn't work. Let's see why. Suppose we start with lock held is false. We run a pink thread and a green thread come at exactly the same time. They will both execute the code for a while lock held. They will both see that it's false, and so both threads will set lock held to be true and return from the lock function. In this case, both threads think that they have the lock. But the rule for a lock is only one thread could acquire it, so this means that this is not a safe implementation of locks. This is actually a very, very difficult problem to solve, and most computer systems at this point solve it with hardware support. Almost all processors now have a special instruction called test and set. Here is shown the code, the C code for what test and set does. It takes a Boolean flag, it first saves the old value of the flag, and it then sets the flag to true and returns the old value. What's important about this is reading the old value and updating it to true are done atomically, meaning that you're guaranteed to return the old value and no one can modify the value between reading it and updating the value to true. This atomic property of test and set is what makes it easy to build a lock out of it. Let's look at how to build a lock with the test and set variable. It looks almost the same. We still have a lock structure with a Boolean variable. The code to release the lock still just sets the lock variable to be false. What's different is that when we acquire the lock, we don't just have a while loop. Instead of a while loop looking at lock held, we call while test and set on lock held. What this will do is, remember, test and set will read the old lock value and then set the lock to 1. So let's suppose the variable was initially false. When a thread comes in, it'll call test and set. It'll set the variable to be true. Test and set will return the old value, which is false. The while loop will break out, and that thread will acquire the lock. When a second thread comes in now and tries to acquire the lock while it's currently held, it will call test and set. It will again set the lock to be 1, to be true, but it will return the old value. In this case, the old value was also true because the lock was held. This will cause the while loop to keep spinning. When the first thread releases the lock, this will set the lock to be false. So when the second thread calls test and set the next time, it will again set the lock to be true, but this time test and set will return false as the old value, and this thread will break out of the loop and return. Note that if multiple threads call acquire at the same time, the hardware guarantees that only one thread will see the value of false returned from test and set. This is what the atomicity property returns. We'll talk more about using spin locks in class. This is the end of part 3, unit on locking. Please take the quiz on locking before going to class.